One of the ways that we can use NMR to help us understand molecular structure is through the different peak positions or chemical shifts that can show up as a result of the different chemical environments that protons can exist in, also known as shielding. So if we imagine a proton, a bare proton, in a magnetic field, this will experience the imposed magnetic field, Bz, and we'll have a splitting of our spin up and spin down states accordingly. Now, let's just alter this scenario just a little bit, and we're going to imagine now that this proton is in a scenario where there are a bunch of electrons floating around. And we know that as electrons move through space where there is a magnetic field, they will curl around in their position, and they will actually induce their own magnetic field, actually opposing the externally applied magnetic field from this north-south magnetic dipole. So these electrons create their own opposing magnetic field. So in the case where we have more electrons around, we will have a smaller magnetic field experienced at that proton because of the shielding by those electrons. This will lead to a lower frequency precession and a smaller chemical shift, which by convention is to the right. When we have fewer electrons, we'll have more magnetic field around the nucleus. Right, this is a bare proton here. Higher frequency precession because we have a greater magnetic field, and precession frequency in that splitting is directly proportional to the magnetic field. And a larger chemical shift, which by convention is to the left. And recall that, of course, our definition of chemical shift is the frequency of the proton minus the frequency of a proton in our reference sample, tetramethylsilane, divided by the frequency of the spectrometer times 10 to the 6. And this gives us chemical shifts in parts per million. So by definition, TMS, CH34SI, always shows up at 0 chemical shift if we're using that for our reference. Something like an alkane will have a similar amount of a lot of electrons around that are shielding this proton, and will show up fairly close to the CH34SI in our spectrum. Something like fluorine. Now our fluorine is pulling more of that electron density away, and as we look at different functional groups attached to our proton, we're going to be moving to a greater and greater chemical shift in parts per million here. So this allows us, at least an initial way, to understand a little bit about the possible functional groups and chemical environment and